So it's a short semester, and just as a recap, what we did so far was 1.5 lecture introduction with the probabilistic method, tree codes, polynomials, etc. And then we did a lot of expanders. This is quite typical in this courses. In the middle, we kind of started with this break, which I didn't talk about material. And then today we are going to start this chapter about pseudo-random generators, starting from the third to the middle of pseudo-random generators, and then in the last couple of talk, like 1.5 lectures, we are going to talk about extractors.
There's 11. Yes, if you count the break, there's 11.
There's 11?
Yes, if you count the break.
We can party. So I can do better. Yeah, good. The more than 11. So today I'm going to talk about PLGs, but I'm not going to mention this one, except for now. This abbreviation, we're going to talk about small bias sets. Small bias sets are pseudo-random generators, and they are used for constructing other pseudo-random generators, but let's study them for their own sake and then I'll give the context. Okay, so today's topic is small bias sets. Okay. So the clear definition, as any good definition, is not very insightful, but let me just write it. So set S is 0, 1 to the n set of strings is epsilon biased. So it's called an epsilon biased set. If for every string, n-bit string, except for the 0 string, so this is like the 0 string, and this false. Okay, so small bias set is a set of strings. Epsilon bias set is a set of strings, such that for any row like that, you can think of it as kind of a linear depth, some vector and zero vector. This thing holds. So what's really written here? So what is this quantity? So you sample an element from the set, uniformly at random, and you check whether this is 0 or 1. So this inner product is either 0 or 1. I mean there's a sum, integer sum, power SI. Right, and you can think of it more true or not because of the -1. Right. Yes.
Isn't this like the character of the K graph?
Yes. So you just ask, how many S's are on the left side or the right side of tau? Like 0 or 1 in a product of tau. And you want, so those that have 0 will contribute are 1, those that for which this is 1 will contribute negative, and saying that this is not epsilon is saying that this is quite balanced. Right? So for example, if S is completely uniform, if you take the set S to be 0, 1 to then, what is this?
The eigenvalue of the character.
No, if you take S to be 0, 1 to then.
It's 1.
0. Right? Yeah, because half of them will give 1, half of them will give 0. It's exactly, it's a linear constraint. So you have the linear subspace of dimension 1 and it's offset. So what we are shooting for here is a set, hopefully small set, not 0, 1 to the n, such that this is still small. Not 0, but small. You can't have it 0 for any test unless it's everything. And you want it for any tau. So for example, if you take tau to be like the elementary basis vectors, here you'll have the ith coordinate of S. So you want each coordinate to be kind of balanced.
Yeah, why isn't it epsilon balanced rather than epsilon?
That's true. Well, I guess smaller the epsilon, it's less biased. Like you want epsilon to be small, but it's in the right direction, right? Epsilon balance means that if it's epsilon smaller, it means that it's less balanced.
Epsilon approximation.
And by the way, with regards to that, if we don't want to, we just want to talk about a small bias set, we call it a small bias set. Sometimes we don't have epsilon, small bias set.
In small normally it's
Because
poly or
yeah. If it's clear from context, it's like it's just a small bias. Like with expanders, if you say it's an expander, you want to say more. So that's a definition. It's a definition. I don't know. It's very insightful, but it's actually a critical definition because one way to put it in context is that the next time we'll do that. So this is an Epsilon bias PRG, which we'll talk about next time. We'll just give you the context for linear tests. Okay, so we will understand what that means later. But that's one thing. Another thing related to what Vin said, really epsilon bias sets are equivalent, completely equivalent to Cayley graphs with respect to the group, the Boolean Q. So the set of generators is going to be this set, but this is the group. So if you have an epsilon bias set, that's unnecessarily homo. The Cayley graph corresponding to it has omega, which is epsilon, and vice versa. It's the same thing, just different ranges. Because these are the characters of the Boolean Q. So really, we're not talking about something new. We're actually getting more specific in terms of Cayley graphs. But really more importantly is that these are building blocks. Maybe as important as expanders, maybe less building blocks of almost all, many PRGs, real PRGs, not for linear tests. So when you want to put something, a class of functions, usually this will be a component in the construction. Either this or that NK-wise independent distribution, which we'll talk about, and or expanders. That's what you have. And polynomials. The polynomials are not objects. You construct this with polynomials. And lastly, the name is a bit misleading because sometimes it's not a set, it's a distribution. I mean, you can repeat elements and so forth. Or maybe there are like non-rational weights for instance. Doesn't really matter. You can always tweak it a little, but the epsilon bias sets are not always sets. Both noting. I mean, when you construct them, you may have repeated strings. And you don't need to worry about it. Just know that it's fine. It's a multiset.
You mean like in the representation?
In certain one?
In representation.
I mean, sometimes when I will construct an S, it will happen to be the case that the same string repeats once. Just is it
just a set with distribution and not necessarily unit.
Right, exactly. So that's a distribution. And then they are called epsilon bias sample spaces, but no one will. That's how you should write it, really. Because you sample from that field. But they are called epsilon bias sets, even though they are not sets. Everyone are all confused by that, so I just want to say that.
Yes.
Okay. Right. To make sure it's all confused together. Good. So the main question, given that they are important and we see they are important, how small epsilon or can epsilon bias sets be?
We know this answer, right?
Sorry?
We know this answer.
He just said me?
Me.
I'm not sure you know. Why should you know it?
Because I mean, like if you take S like in a similar manner to the Van der Munde one, like with the, and then you look on the roots of the polynomial, then you can take it.
What polynomial?
What's there? Okay.
I think you're referring to one of the constructions, but it doesn't mean that it's not the best. We'll talk about it. But we want small bias sets small bias sets because we were going to sample from them and we want this set to be small so that the number of analytics will be small. So definitely 2 to the n is a 0 bias set, it's optimal. But given that I'm shooting for an epsilon, I have another parameter, how small can I make an epsilon bias set? So no one knows really completely. There's a lower bound, which we will not prove. It's not that difficult, but it's going to take time. There is the probabilistic construction, of course, which we will do. I don't like the probabilistic construction. Don't construct it. argument.
Probabilistic couple.
Proof of it. Everything is better than that's why it is proof of existence. And then there are constructions, higher, but they are good constructions. Very good constructions. So the lower bound is n up to constant, right? Divided by epsilon squared times 1 over log 1 over epsilon, which you kind of should ignore a little bit because that's the main part.
Log.
No log n. So it's linear in n.
Oh, it's log of 1 over epsilon.
Yeah.
I thought it's
Right. So it's so the okay. To compare the probabilistic method will give you n over epsilon squared. So that makes sense because that's smaller than that. Because you divide by something which is larger than 1. Like initially it's no, it's fine. And no one knows where the truth lies actually. And construction-wise, there are plenty. The original one by now I know was n to something. And then they got it down. Then there were a couple of constructions that did this thing. So it's optimal in n, so optimal in epsilon, or I don't know if it's optimal, but ignoring that. And quadratic in n, which is kind of bad in that sense. Sometimes it's a killer. Sometimes you can't do that. You have to have an n, but sometimes you don't. And then there were other constructions, like there's a weird construction that has this thing. So it's a probabilistic method to 5 quarters. You'll see that. And then there's n over epsilon cubed, which is actually quite difficult. This is using AG codes. This is also using AG codes, but it's similar.
What is AG called?
Algebraic geometry codes.
Okay.
This is the free construction that does that. Let's see one. You'll see one in the homework. You'll see one today. And this is using expanders. Now the cool thing is that I don't know if it's cool, just it's for me. I mean, it's something about me. Not so when I saw this construction by Alon Tashma and Avi Ben Oya, it's really beautiful. It uses AG codes in basic way. So I saw that and I said, it's really cool. I want to learn this. I learned for years. It took me time. I invested so much effort because the expanders give you kind of a cool result. Don't take them seriously in that regard. And there was another construction. It was a homework question, repeated sometimes, which gives you n over epsilon to the 4th. Essentially, doing this the best way possible with expanders. And that's using expanders, but carefully. And it's worse than even that, so I didn't care. But what Amnon noticed in a follow-up paper to that one, I mean, after he redirected me in the wrong way, we're doing edge codes, he noticed that with expanders, you can actually, like, not trivially, do almost optimal. And this little one is really little one. It's 2 to the square root of log and something small. So it gets essentially the right detouring everyone else with this beautiful paper. But this was actually before that. So what we will do is we will do of course that's going to be easy. It's a probabilistic method, it's a one-line proof. And then we are going to do one of these. And we are going to do another one of these. And interestingly, even though this is difficult, if you are willing to pay a log n or maybe log n over epsilon here, that's not so hard, given that. And that's in the homework. So we'll do this. And then I'll ask you to do a log in here using that. With a hint, otherwise it will be difficult. So that's everything. That's the world of epsilon bisets, construction wise. Okay. Using them is a different thing. Many more people uses them in construction. Otherwise, it won't involve the wire. But are we clear on what are epsilon bisets and what are we shooting for in terms of size? Questions in general?
I wonder if from the expander solution can we reach the lower bound?
I mean, we currently can't even reach the probabilistic method. I mean, there is a gap between that.
Because like even though like Because there's like the log 1 to the epsilon. So maybe could be like a trade-off. Because if you take like.
But again, with the expanders, you can't even reach yet this one. It's larger because we divide by the power of epsilon rather than log numbers. No, yeah, it's a slight, somewhat deep question in terms of coding theory. Okay, these are relations to coding theory, and also we should maybe this to be my second bullet or so, but they are very much related to codes. These are actually stronger than codes. They imply codes. You will see what happens. For now, so you see, they try to carry graphs into codes and they have many applications. So and it's kind of funny because the definition doesn't seem like they have a promising future. It's like -1 to tau s is small. The reason, by the way, that it's so useful is because Fourier analysis, because you can decompose any function to this basis of characters, and once you fool the characters, you fool many functions, like, depending on their weights and so on. But the application of axiom bias are actually much more elaborate. So let's see this one example, exactly one example actually. So let's do the proof of existence. Thank you, guys. But that's really easy. I mean, what should you do? The only thing that's confusing is that, okay, I don't know. Okay, what should you do?
Pick S around.
Pick a random S, exactly. I mean, the only reason it may be confusing is because if you think of S as something you sample from, then it's a function that gets log size of S bits and output something, and then feels weird to sample something that sampled something. So that's why it's better to think of it as a set, like I'm doing it without confusing everyone. So and when confusing everyone by saying. But I'm going to pick the set at random. Let's have size M, and we'll figure out that M needs to be that size. So let's pick just M strings at random independently. But these are sampled uniformly and independently.
So it's a multiset.
Right, so it's a multiset, even though you can bound the probability of collisions, put it linearly bound also, so you can get a set. But yes, it's a multiset. Because it's going to be so small, way below the square root of 2 to 10, so there will be no collisions. Okay, and then, okay, we picked it, now let's see if it works, right? So against what we have to check our set? Right, but given a tau, right? So fixed tau, this is going to be an inbound of the taus. It's a non-zero tau.
And then we'll take minimum bound to show.
Right. So the point is that tau si for every I. It's okay. So -1 to that. What is its expectation?
It's so.
Right. So si, I'm choosing si uniformly at random, like for fixed time. S1, S2. Uniformly at random from 0, 1 to the n. If you want to choose it without the 0.
Yes, 0.
That's actually fine. And as we said, half of them are to the left of tau and half of them to the right. So expectation is 0. And because half of them are 0, half of them are 1. Good. So if we call this, II. Sure. So if we call this II, then we can ask what's the probability. So that's one thing. That's one FC. But we can ask what's the probability that there is a deviation from the expectation. What's the probability that the sum, maybe that's divided by m, is really the expectation. This is really what we care about, the expectation of this. Over, like this is the expectation of -1 to tau si. I from 1 to n. If I sample I from 1 to n, this is the quantity that we care about. I'm averaging over all SIs. So what's the probability that this is most as at least epsilon, or maybe absolute value? Right, that's exactly the quantity I care. Because because I'm averaging over the SIs and asking for each what's this. So do you know this?
Yeah, it's time 2 times x of there's a lot of variations. I know the -2
Right, I'm just going to do this without the constants. There is a constant here, but essentially speaking, if you ask, deviation from average here is 0, so it's nice. If you wanted to bound the deviation of average by epsilon, then the probability that you will have this deviation is proportional, exponential, and then proportional to the number of experiments you make, epsilon squared. You should expect this epsilon squared. This epsilon squared comes from the fact that it's not standard deviation. You are expecting that to have, like, if epsilon is, if epsilon is a lot smaller than 1 over m, you don't 1 over square root of m, you don't expect to get anything. Because in the standard deviation regime, things actually do happen. Right? A binomial, right? In the middle, the binomial coefficients are actually large and roughly the same size. But when you deviate, you expect, when you ask for deviation, large deviation, you expect it to be small. And this square, this 2 is the 2 that will hunt that 2 and every 2 you can see, including, but it's more complicated there, I think, in experiments. It's the reason for the square root. But so this is the 2, some deviations. Okay, so what should we do with this number? When it's a small number, that's good. So by the union bound, so this is the probability that our sample set will fail tau with respect to tau. And there are 2 to the n terms.
Minus.
Yeah. So the probability that S is bad, namely that it fails to 1 tau at least, by that I mean fail for some tau, right? Regardless of the relations between them, there's always 2 to the n or -1 really, but that's fine. 2 to the minus omega of epsilon squared m. And if this is smaller than 1, we are happy. Because this means that there is a set for which it works for 1 tau. And once there is one with no additional cost, really, you get the most sets out there. And so it's enough that m will be like, some of. But again, the crucial thing is the square here.
can make it better, like on the lower bound or not? Like,
So that's the best known proof of existence. For the lower bound, actually the lower bound uses some eigenvalue arguments. So you construct a big, I wanted to do it, but then I decided to take like 20 minutes, which I don't have. But it's really nice. It's a proof of Noga, so it's always nice. Maybe, let's see if I'm not sure. Okay, let's do it today. So we did this proof of existence, and now let's do one of those. And the problem with this construction that I'm going to show you is that if we had more knowledge of coding theory, it would have been more apparent that that's a good idea. I'm just going to give you the construction, but really what happens behind the curtain, and they didn't bother putting that in the paper, is that they concatenate the Reed-Solomon code with the Hadamard code. That's what's happening here, but I'm not going to say that, other than just no. So here's the construction. So it's called the power range construction. It's beautiful, but after you understand that it's just concatenation, it's kind of maybe that's why I did it.
Good magician, never.
Right. Yeah, I wonder because on the paper there's no guy around which knows coding theory. Oded Godrai, Hassan, and Peralta, which I don't actually know. These are big people.
Yeah.
They know. So I wonder, maybe they wanted a self-contained like one-line proof or something, which you get.
Yeah, but then you say.
Right, you should say.
You could see.
Right. Yeah. Took me a while to see. Okay, so I want to construct the set. So I'm not going to name the index of the sets by like vanilla integers, I'm going to use a field elements. It's kind of related to what you said. So we are going to have this field. Let's fix a field FQ, finite field. And I need Q to, and it's more convenient for it to be a power of 2. So these are not like simply like finite fields. It's very like. Okay, and now the elements of the set are indexed by a pair of elements in the field, by x and y. X comma y, these are 2 elements in FQ. Okay. So the thing we are seeing is x, s, x, y. That's a string. And our set is all of those. So its size is what? Yeah, 2 to the 2 actually, right? Because it's a square. But let me just say q squared because I don't really need the images. Okay, so that's the size of the string, and so it's a square of something. So you can see what q is going to happen, it's going to be in the upside. And the cool thing is that how we define it, like so s of xy at index I, and now the index for me is really a number. That's fine now. So this thing you should think of as a number between 0 and n minus 1. Or 1 to n, right? Same. Right, so that's the I coordinates of the set. This set definitely lies in 0, 1 to n. So choose. So you're doing the following, it's really cool. I mean, if you haven't seen this. So you take x and take its I power in the field. And then you think of it as a vector, a length L vector of bits. Because you can. Because if you have a finite field and it extends another field, it's really a vector space only. So that's a vector space of dimension L over F2. So you can think of it as a vector. So I should write like vector something, but I'm not going to do that. There is an once you can fix the description of the field, there is one way of doing that. And then you're going to take the inner product with y. They get also thought of as not as a field element, but a vector over F2. So this is inner product in F2 over in F2 2D, not F2 2D, F2 2D.
And that's the other one.
Right. So that's hiding grid. So it's not completely clear, but that's definitely other one. If you know this things. If you don't like this going back and forth, when actually correlation-wise you won't even like the other things just now, but you can also do work with fields exclusively. It's not equal. You can just do that as well. You can take the place of x to the I times y. If you know what it is, it's another way of taking an element in a field to an element in F2, some field, which doesn't involve like moving to bit representations. But so some people like it, some people don't. Same proof would work. One thing that's important is it's bilinear. But you don't have to do that. Just if you don't like moving from bits to field elements, then you can do that. It's cleaner. But that's more computer science.
To think like concretely on the trace, you do go exactly.
Right, exactly.
The
We
same
need to
thing.
choose the
You do
representation.
exactly.
Exactly. That's true. Every trace is a real product of some sort. It goes way beyond finite making. But what I like about this is if you think of the pseudo randomness thinking, you have a bit stream, and if you ever thought what happened when you think of it as a field element related to the I power and get back a bit stream, it looks random. Like for us human being, you have a bit stream and you have a representation of the finite field, so you think of it as an element, so you can multiply to kind of multiply the vectors in a sense. And then when you go back and parse it as bits, it looks really weird and random. So I don't know if it's helpful to anyone, but it's a very non-linear thing to do.
It looks like it's not random enough because we didn't stop that.
With the Y. Or,
Yeah, like you need the y somehow. So
yeah, one
probably
bit.
not
Yeah.
random enough. Yeah.
Yes. Again, yeah, all this. So it's not random as a field element, but when you hit it with a random string, it's like, yeah, in a sense. Okay, so let's analyze this thing. So one line, the construction is it. So what I need to do is to take a tau and look at this thing. Without the absolute values, the absolute values. Right? Since our set is indexed by these field elements, I just need to go over this expectation. I should take the absolute value, but never mind that. And let's zoom in on the exponent, because that's where the action really happens, right? So this thing, let's write it down. So it's the inner product between tau and Sx of the what's written there. So it's the sum. I goes from let's start with 0. Because I started like that. Tau I Sxi I. But now the point is that Sxi Sxyi I can write as I can't write tau like that. Tau I, and then you have the inner product between x to the I and y. And it's only integer, so think of this inner product over the sorry, that's what it is. So I said to think of that as inner product over the integers. Now what should you do? When you have a something with a function which is linear and you sum over it, replace it, right? Just apply it on the whole thing. So swallow the sum inside. By the way, at some point that should remind you of something you did. So that's I goes from 0 to n minus 1. This is the inner product. So you did it in column set. Column 5 in the column set for degree 2 polynomials when you constructed k-diagrams. So I'm doing the harder work for it. So this thing, if you look at it for a second, what really happens here? So the thing you're trying to understand its bias, after you take minus 1 and so forth, is it has a part that the adversary controls, the one that picks up the adversary controls, and the part that it doesn't. So if you look at it for a second, this is like a polynomial chosen by the adversary and evaluated at x. That's what's written in here. Right? And then you take the inner product with 1. So, okay, so the whole thing. So if you look at it for a second, what really happens is that the construction forced the adversary or translated the adversary to someone who picks the polynomial. And now I'm happy because x and y are completely uniform. So, if x is not a 0 of this polynomial, that's a non-zero field element. And so it's a non-zero vector because there is a bijection between them. And since this is a non-zero vector and I'm going over all possible y's, this is going to be unbiased, completely unbiased. Right? So if x is not a root of p tau, we are happy because zero bias. So if you consider this as first as expectation over x and then over y, then when you do the expectation over x, every element in that expectation, when you go over all y, you get a 0. You're complete balance. Zero bias. And if x is a root, then what do you get? Right.
It's 0 in the 0.
0 in the exponent. Right. So minus, let's write it like that. So the big one. The minus 1 to the 0. So it's always actually biased in the same place. Yeah? So that's good. That's actually too good. I mean, usually you don't want to have such a good case and then a bad case, but that's good. That works. Okay, and so what's the question we need to ask?
How many roots?
How many roots? Yes, how many roots do we have? Because every root is
At most.
n
Minus 1.
at most n minus 1, right? The degree. So there are most n minus 1 roots. And so the bias, so this thing, I'll write it. So, you know, you average over Q squared things. But, you know, doing the expectation over X force, you know that N minus 1 out of Q will give you a 1, at most N minus 1, the degree, the number of roots, but it's bounded by the degree. So the probability that X will fall, will be a root of P tau is at most this. And once this happens, you get a 1, otherwise you get 0, so that's really a bound on the end. Let's call it as N. Something going on. Okay, good. So if you call this thing epsilon, you know, you say I know that the bound always satisfies that, then you see that Q is at most N over epsilon. Q can be taken to be N over epsilon, and it's enough to take Q to be N over epsilon to make this form works. And then the sample space size is Q squared, which is what we want. So this SSS is sample space size. It's Q squared, which is N over epsilon squared. That's it. Instruction. Any questions about it? Is it too fast? Or
It's very simple.
it's very simple. It's really simple, but really it's a code calculation. And once you have this, if you kind of understand this enough, it's obvious that that should work. Because really what happened, we used the Reed-Solomon code over a large alphabet and then cut it into a binary code, and every non-zero symbol translated to bits which are actually evenly and so forth. But I like this construction in proof because it's just like it's
Why thinking of it as concatenating means that we should know that it works.
because when you concatenate it, you have a code over a lot of large symbols, and then you want to reduce it. So you take another code that its size is the symbol size, and so every symbol which is non-zero in the big code, because of the Hadamard is as a perfect kind of balance, it will give you a perfect balance between the bits, because you take all possible linear combinations.
So Hadamard is actually the one that we want, and the
Good.
Reed-Solomon is the one that we end up using in order to utilize Hadamard.
I don't know. I mean, Reed-Solomon used in order to make sure that there will be not too many zero symbols, and every non-zero symbol was a complete success. And Hadamard is a choice. You can make another choice. Also for Reed-Solomon. Actually, that's what I want to do. Now let's do. I'm not going to do it completely. I'm going to cite things, not even formally. Let's do this. By the way, the story here is that Avi and Amnon had this idea of using AG codes in a non-trivial way. N over epsilon cubed is trivial given AG codes. AG codes are not trivial. So they wanted to use AG codes in a non-trivial way.
What is trivial?
Like essentially what we did just now.
Okay.
But if you have AG codes which are non-trivial, instead of Reed-Solomon codes, you will get N over epsilon cubed. But they used AG codes in a non-trivial way. And they used actually the most trivial AG code in a non-trivial way and got this. And when they said, well, maybe you can get like, so this is 1 plus a quarter, right? So when they said, you know, maybe I can use another AG code in a non-trivial way to get that. So deltas are smaller and smaller. But actually that's impossible. It turns out that with AG codes, you can formalize in a meaningful way that this is the best you can do using AG codes. You can just throw away the AG code and do what you want, but in a meaningful way, there is a limit. Anyway, that's the story, but that's what we'll do.
And did they get this in?
No, it's a lower bound for these kind of constructions, but they don't have a curve that gets them. And maybe there is another lower bound. Maybe that's the best really.
What is AG codes?
AG codes is algebraic geometry. Yeah, I just mentioned it briefly at one point. Okay, so how do you do that? It's very similar to that in Spirit. I mean, the first thing that you should ask yourself when you see that is, or if you know the codes perspective, you say what happened if I take read mu level amount or something like that. And it will give you something incomparable with that. You take derivatives, something else, it's a fun thing to play with. But they use the Hermitian code, which is really nice. I'm going to do that. And again, I'm not going to look at the coding perspective, even though I'm giving it a lot of time here. I'm just going to do it immediately. So now our SS will be indexed by 3 elements. X, Y, and Z. Not just X and Y. And X, Y, and Z will be field elements as before. But technically, I need Q to be not just a power of 2, but an even, like in that sense, power of 2. Every power of 2 is even powerful. And other than that, I'm going to do roughly the same as I did before. So given that this is the indices at entry I, J, so now I'm not going to have indexes going from 0 to n or something, but rather a couple of indices, a couple of things that go roughly the square root of n, we'll see. I'm going to define this to be the inner product between xy, ij, and z, x to the I, y to the j, and z. But I'm slightly cheating. I mean, these are indeed elements of FQ, but x and y are not going to go over all FQ squared. If I'm leaving this and that, then that's essentially being like a read-muller version of that. It's a two-variable thing. You have the free variable, and now you have 2 variables. So instead of that, that's fine, but it's not going to be the whole story actually. X and Y and Z are going to be from here, but I'm going to only consider exactly. And then to be specific, all the X and Y's such that Y to the P is 2 to the L, is the square root of Q. Y to the P plus Y is X to the P plus 1. I know it's good coming from nowhere, but the idea is that I'm choosing what's called a curve. So I'm taking all X and Y's, satisfying this in FQ.
Haven't you seen that in one of the first lectures?
Yes, this is the Hermitian curve. So let's call H this set. Let's call this set, denoted set by H. And I mean, this is in F, X and Y are in FQ. It's a carefully chosen set. I don't know if you know enough about finite fields, definitely algebra and something, but this is really the trace from FQ to FP. And this is the norm from FP to FP. And we can talk a lot about these things. Not we, but there's a lot to be said about the time. There's a lot to be said about it. But the cool thing about this thing is that the size of H, not D thing, one good thing is PQ. It's not D, something. Right, so we are living in a Q squared world, P to the 4th and 4. X and Y live freely in FQ times FQ, Q to the 4, Q squared, P to the 4th. And of course, there are at least like P solutions to that, like kind of mainly, but or Q even, but P times Q or P cubed, it's not completely trivial to see. And the idea is just that, the bottom line is that for every X in FQ, turns out that this lives in FP. It's a norm, it kind of reduces elements from FQ to FP. And that's also the case here. And this is a linear function in Y, even though it doesn't seem like that, it's linear in Y. So really, for every fixing of X, you get a linear equation over FP, so you have like 1 out of P solutions. So for every element here, for every of the Q elements, you have 1 out of P solutions. So it's Q times P or PQ. That's kind of just not, I'm not going to prove it. I'm not going to prove something much stronger than that in a second. That's nothing, we can do that. But that's just one concrete choice. And then let's see where does this analysis that appear there takes us. You'll start the analysis and then you'll see you need a clearer. And that's the beauty of supermodel, that it uses like reports a lot of mathematics. So analysis it's the same analysis, but here at this point we'll use the fundamental theorem of algebra. Polynomial doesn't have too many roots. Here we'll use something else. You'll tell me what it is when we get it. So let's start. I need to write this expectation, but let's just consider the exponent. That's the only thing that matters. So tau s x y z. Let's start with this. That's the exponent. So yeah. So I plus j. I need to produce n bits. That's what I'm trying to construct an epsilon bias set of n bits. So I plus j. I need to say I'm going to take all I and j such that their sum is r, post r, like total degree. Then you can see that n is roughly r squared over 2. I mean, if I'm bounding their sum by r, it's like the binomial thing, r plus 2 choose 2. Then and I want n outputs, and there's like that, then this is the relation. So I need r to be roughly square root of n. It makes sense. This square root of n, this square root of n. Okay, so you're summing over all I and j, such that I plus j is most r. And then you're writing tau ij, because everything is in the standard. X to the I, Y to the J, Z.
Same trick, right?
Same trick. Like this in, that's really the Hadamard speaking. So far, we are not using the code itself, just using these things, which is really the Hadamard, choices of the Hadamard. So maybe let's write Z before, less action. Okay. So what do we see here? What is this? We call that PT of X. So what is this?
As you said, remove.
Right, but we're not working over the entire XY. Right? We're only going over XYs which as a pair are in H. Right, but this is really indeed a polynomial in X and Y, or in a fixed X and Y. That's fine. And now when you take the expectation there, that when you do that, we're going to do -1, this, and going over all X, Y, and Z. Well, X and Y are in H, and Z is uniform. Or FQ. Then, what I'm really asking here, when I take the expectation here, is that, again, if XY is a 0, if XY chosen from here is a 0 of this polynomial, I'm in bad shape. Otherwise, I'm completely happy, as before. So the only problem is roots of this polynomial that are also on this curve. Right? So we lose, let me lose for every point of intersection of H and the roots of p tau, right? For every root of p tau, so the roots of p tau also form a curve. For every root of p tau, which is on H, I don't mind otherwise, I'm losing because this root will give you a 0 here, and all the z's will give you the same thing. So that's the only problem. So if I didn't use like this H, just regular, my problem would have been the roots of p tau. That's I can bound by Schwarz-Zipper. We can do that. But here I'm doing something that's actually stronger. I'm asking how many roots does this curve have in intersecting with? So how many intersections does this curve have the roots of p tau with H, which really are the roots of this polynomial? No, not one. Oh, sorry, I want to conclude, but do you know the theorem that says if you have two curves and you want to bound the number of intersection points? It's a French, except for Thomas, of course. It's a Vesu.
No.
There's something here. But Vesu is and it tells you that unless there is a non-trivial component to the two curves, the number of intersections is of course the product of the degrees. So so we will lose so number of intersection points is at most product of degrees, and the degree of our curve is p plus 1, but let's call it p. It's the not completely accurate, and the degree of p tau is like r. So this is the number of points we are losing, but it's, you know, if you take the expectation over h, you need to divide that by the size of h to get the probability that you, the fraction of x's that you, of xy's that you are losing. That's the absolute number, but I don't care about the absolute number. Like here, I divided by q. Now I should divide by the size of h. And if it's okay that I'll take 2 minutes of your time, I'll just conclude the.
And that's when you get R divided by Q again.
Yes. Yes, exactly. So the error is at most PR over the size of H, and because these amount of the points of H are traveling, so that's the fraction wise, which is PR over P cubed, which is R over P squared, which is like something like square root of N over P squared, because R is something like square root of N, maybe 2 square root of N. And what's the sample space size? This times that, right? It's H times FQ, or H times Q. And okay, H is, let's do everything in P's. H is P cubed, okay, and Q is P squared. Right? So all in all, the sample space size, so from here you see that P squared is square root of N over epsilon. So P to the 4th is N over epsilon squared, which is what you want. And you get that to the power of 5. Like, so it's N over epsilon squared to the 5 points. Well, next time we'll actually see we'll start doing like more complexity things with the construction, not constructing more. It's a different flavor of things.